Welcome to our E-Innovista program. In this session, we will discuss the topic root locus in LabVIEW. In this session, we will also explore the fundamentals of the root locus and its application in control system design using LabVIEW software environment. So get ready to dive into the world of control system and learn how to analyze and design system using root locus techniques in LabVIEW software environment. So let's get started. About introduction of root locus, it is the locus of the roots of the characteristic equation of a feedback system as the system parameter typically gain varies it at all. It helps in the predicting the movement of poles in the S-plane and understanding the system behavior. Here you can see a transfer function that numerator part is k in multiplied by s plus 3 and the denominator part is s plus 1 multiplied by s plus 2. So we know the transfer function is output by input. In this way, we put this equation and the numerator and denominator as well as. So here first we need for the root locus, we need to define the poles and zero value for the transfer function. So at the denominator part, from there we need to collect the poles value. That poles are s plus 1 is equals to the 0, that s equals to minus 1, as well as the s plus 2 is equals to 0, s equals to minus 2. There are two poles, and the numerator part, it is the zeros part. There is one number of zeros, that s plus 3 is equals to 0, s equals to minus 3. So there are two number of poles and one number of zeros are present as an example of this equation. And the construction rule for the root locus, the k is equals to 0 points, that minus 1 and minus 2, and this is the two are the poles value, that n equals to 2, that refers to the poles number, and k equal to minus infinity points, that minus 3 to infinity from this range, and n equals to 1, it's referred to the 0 number of points. So the number of branches here is 2, and asymptotes is equals to the 2q plus 1 pi by n minus n. So the number of asymptotes here n minus m, here n is refers also we define that n is refers to the poles and m is refers to the zeros. So n minus m, poles minus 0, that poles 2, and m is 0, 2 minus 1 is equals to 1. So number of asymptotes is 1 and the theta is pi. So the next is the centroid. We measure the centroid for the root locus into the graphical representation of the root locus point, that intersection of asymptotes. So sigma, the centroid refers that minus 1 is and minus 2 is the pole. From there the minus is minus 3, there are zeros point, and 2 minus 1, the number of poles and zeros. Difference between the number of poles and zeros is 2 minus 1. So the centroid value is here 0. And then we need to root locus on the real axis between minus 1 and minus 2, and then other is the minus 3 to minus infinity. Root locus on the imaginary axis in the characteristic equation, we also know that the 1 plus GSHS is equals to the 0. From this equation, we need to the characteristic equation that s square plus k plus 3 multiplied by s and 2 plus 3k is equals to 0. From Rao's stability criteria, we need to define the k stability value, that s square s to the power 1, s to the power 0 according to this order. The Rao's stability criteria you may construct, and the for stability k must be greater than minus 0.66. Root locus never intersects imaginary axis. Next, we move to the breakout points. In these breakout points, we from the characteristic equation, that dk by ds, from the differentiation, you need to put the value that s is minus 1.59 from this equation. After the differentiation, s's value is minus 1.59 and another is minus 4.44. S is minus 1.59 for this value, the k's value is 0.17, another s's value is minus 4.44, the k's value is 5.8. Therefore, s equals to minus 1.59 is a valid breakout point, and the s equals to minus 4.44 is a valid break-in point. So, we're moving to our LabVIEW software environment to explore the root locus, how it can be constructed. So, moving to our LabVIEW software environment at first. So, there is the block diagram, and this is our front panel. At first, we need to create the transfer function. So, right click on the block diagram panel, then going to the control and simulation. Into the control and simulation block, you can find the control design. Into the control design, model construction. Inside this model construction, you can find the cd construct transfer function model.vi. So at first, it's put this. Then we need to define the numerator of the transfer function that create control, and again we need to the denominator value create control. So as well as next is our CD draw transfer function. So right click again the block diagram window, going to control and simulation, and then control design, model construction, CD draw transfer function equation. After that, the wire can be joined the CD draw to CD construct function model. Then it can be right here, click and create indicator for the transfer function you can produce. Transfer function equation, and the front panel you can see that new numerator array palette can be generated, and also the denominator array palette, and again the block is generated, that is equation, that name here the transfer function equation. If you put the value of this one is the denominator and this one is the numerator. Suppose you put the value 2, 3, 1 and denominator part 4, 7, 3. So after that you can run this VI. Your transfer function equation is s squared plus 3s plus 2 divided by 3s squared plus 7s plus 4. This is your transfer function equation for this program. Now we need to create the root locus for this transfer function equation. So right click again the block diagram window, going to the control and simulation, control design, then going to the dynamic characteristic. Into the dynamic characteristic block, you can find there many functions that cd root locus.vi, cd pole 0 map, cd poles.vi, as well as cd 0 damping, various function also present. So here we need to require the cd root locus.vi. So at first it is present here, put this function and control H the information of this function. Then here select the state space model, either state space model and either the transfer function. Next one is you can output as a get root locus graph, root locus data, root locus information. The three types you can find as a output. So at first it tends to be transfer function. Then it is connected the transfer function to the root locus. First you connect it, then right click here, create indicator. That's first one is root locus graph. Next is first one is the root locus graph. Next one is the root locus data. Next is the root locus information about many other functions. So this is our construct model into the block diagram window in the LabVIEW software environment. After that, run this VI, the continuous run. They can be plotted. So from this value, the value of the graph is very small. So we need to change the numerator and denominator value. So suppose we put 3, 2, 0. So there is a transfer function equation. It is change that 2s plus 3, 2s plus 3, 3s squared plus 7s plus 4 in the denominator part, and the numerator part is 2s plus 3. So after that, the graph will be generated here. So after the graph analysis, again the root locus data, that it is our root locus data, and into the below the root locus information also be present there. So analyze this equation, that the graph will be root locus graph will be plotted, that imaginary axis by real axis, and this is our root locus value, and the root locus data, the k data plotted, and roots value also be plotted there. So in this LabVIEW software environment, also just we need to require the numerator and denominator of the transfer function value. After that, the graph will be also be generated into the software environment as the functionality. So in the academics that we need to require the graph paper, log graph, that plotted the root locus, asymptotes, centroid, poles, zeros concept, but there is no anything present, just only put the numerator and denominator of the transfer function equation, and after that the construct model can be joined, and then you can put this result, you can view this result that has a root locus graph and the other parameter of the root locus present. So hope you are enjoying this session, and again for the future videos, if you need to the step-by-step guidance, if you need to the step-by-step guidance, subscribe our E-Innovista channel for upcoming updates. Thank you.